Hi, my name is Matt, and I wanted to do a quick talk on the map interpretation of attention. So attention, is a really popular thing in NLP at the moment, and I think it has this really nice way of thinking about things in terms of a map that I wanted to share, at least the way that I think about it. The way I wanted to do this talk was to go through, an old problem in NLP that sort of was causing some grief, show how attention was used to solve that problem. Particularly using this idea of how the map interpretation goes. And then at the very end, we'll just sort of do some modifications to that thing to show how it's the basis of an architecture called transform. So let's go. So I want to start again with some NLP pieces. And one of the simplest problems in NLP is this idea of pos tagging, so parts of speech tagging. And in parts of speech tagging, where you take some input sequence like this one, I really like cheese, and we try to output a series of parts of speech for each of those tokens. So I really like cheese, in terms of parts of speech tagging, gets converted to a pronoun, an adverb, a verb, and a noun. And the reason I say this is simple is because this is like the classic RNN type problem where there's a one-to-one correspondence between the inputs and the outputs. So I've got two sequences that are both the same length. And if you think about where the information flows in a network like this is the common important way of thinking about networks. I think the main part of the flow is this vertical flow from the input tokens directly to the output tokens. And so generally each of these words corresponds to a particular pos type, which is what the network sort of learns. And then this intermediate layer, which talks about the sequence, this hidden layer, really captures the exceptions to the rules. So in terms of information, it's mainly around the token to the part of speech, with this hidden layer representing, cases where it should be maybe a little bit different. So that's a classic application of a recurrent neural network. But when we think about translation has a similar sort of property that we're doing this conversion of a sequence to a sequence, but it has this real subtlety that often the number of tokens isn't the same. So we might have, in this case, I've got some English to some Spanish, and my input sequence has 5 tokens, but my output sequence has 4 tokens. So even though generally there is roughly this one-to-one correspondence between the input and output tokens, we can't use this direct connectivity because of this idea that we may end up with a slightly different number of tokens. So there are a number of different ways you can sort of try to handle this temporal alignment, but a really popular one is a model called sequence to sequence. Now, in the sequence to sequence model, the way of approaching this problem, we decompose it into 2 parts. There's an encoder and a decoder. Now, the encoder's job is to take that original input sequence and compress it into one representation. And that one representation then gets passed to a decoder network as context for doing the decoding. Now, this has the pro that we don't need the same number of tokens anymore because everything is going through this bottleneck. It's sort of independent how many inputs and outputs we have. It has a big con though, which is the same con, the fact that everything needs to go through this bottleneck. So in terms of information flow now, there's a lot of pressure on this one link here to fully summarize the sentence, which is a little bit different to the last one where, the flow was at the token level from input to output. So that's a big con. And the use of attention was the first sort of way I saw this solved in an interesting way. So let's, in what feels like a bit of a context switch, talk about differentiable maps. We'll come back to how this idea is helpful in this sequence-to-sequence problem. And I'm going to go through some code snippets. I'm going to use this little helper function JA that sort of wraps a list of lists and turns it into an array so that we can do some linear algebra. So this is just a little bit of functionality we'll be using. So let's think about one way of representing a map as a pair of matrices. One for a set of keys and one sort of for a set of values. So this key and value pair of matrices here corresponds to a dictionary with 4 elements. It's 4 elements because each of the keys and each of the key and the value have 4 rows in them. Now each key in this setup is a 3-dimensional key, so it's a little vector, and each value is a 2-dimensional key. So this is there's many ways of representing a map. This is one way, and the only real sort of assertion we need to make about this is that the number of rows in the keys and the values match, because there's this idea that for every key there is a value. So if I had a query which is a vector, I can look that query up in this map. So what would that mean in terms of how we think about maps? Well, what I want to do is I want to find the key that matches this query. So this would be this first key here, and then return as sort of a lookup the corresponding value. So because this query matches the first key, I want to return the first value. So one sort of odd way of doing this, based on how these are structured, is with dot products. So what I can do is I can take this query and I can dot product it with the transpose of the keys. So what I'm doing here is basically saying a row-wise dot product between this query and keys. And that gives me this sort of what I'm calling here scores. This can go by lots of different names, scores or affinity. I'm going to use scores for now. And what scores in this case says is that this query matches directly this key. And I get this one value when I do that dot product. And when I dot product this query against the other keys, I get zeros. Now, I can use this scores as a form of looking up in the values, again with the dot product. So now what I can do is I can dot product these scores versus the value. And because I have this set of values here that is 1 for the first value and 0 for the others, a dot product does that idea of extracting that as a lookup. So this is what I wanted. I wanted this query to match this key to return this value, and that's what I get through these. Now, the way I've sort of structured these numbers here means that it works for a couple of particular reasons. The first one is that the key and the query here are both unit length. So when I take two things that are equal and I dot product them, when they're unit length, I get a 1. That's how I got that 1 there. Another thing is that the query and the other keys here are all orthogonal. And when I dot product orthogonal things, I get 0. So that's how, I was careful with the selection in this case of the keys and queries so that I get this exact sort of thing I was looking for. But that idea of the constraint around the unit length thing can be pretty easily removed with normalization. So let's think about how if I have some keys that are the same now, but I've got 5s instead of 1s. If I have a query that again corresponds to the first key exactly, I can do this same sequence. I can talk about the dot product, so the query times the dot products. But the problem is now that because these query and key weren't unit length, I get 25 here. Yeah, the other ones are still orthogonal, even though they're all 5, so I get the 0. But I want this to be a 1 to correspond to that lookup. So it's pretty easy. I can just normalize. I can just literally normalize across this to make sure that this adds up to 1. And then I get the same thing I wanted before, but I can take these normalized scores now and sort of multiply them and dot product them by these values and extract them. So that's cool. Now, this was an example where the query matched one key exactly. So I've got this 1 and these 0s to do that lookup. But the whole point of this attention mechanism with these vectors is you can get some interesting sort of combos of these lookups. So let's look at a couple of those. Firstly, what I'm going to do is I'm going to wrap this thing we talked about so far into a little function, so I can call it a couple of times. This is just the same steps we had on the last slide. And let's think about a couple of different lookups. So firstly, this query, 050. Now, that actually turns out the way I've done this is that it matches 2 keys in this keys matrix. So that's interesting. Normally when we think about a map, we might think about maps having keys that are distinct, but we can sort of relax that a little bit here. And what would we think we would want if we had a query that matched multiple keys? Well, let's see what this function does. I think it's quite intuitive. We end up getting the scores, which again are 25 and 25 because of that dot product being exact, and 0 for the orthogonal ones. And after the normalization, we get this half and half. And that's interesting because when we get this half and half and combine it with the values, we actually end up averaging these two values. So I've matched these middle keys exactly. And what that results in terms of a single return, in terms of a lookup, is this averaging. And this is why we call it a soft lookup. It's not this hard sort of exact query to exact key to exact value. Because of this idea of the dot products, we get this sort of things like averaging. Now let's look at another example, which is a different, slightly different. This is a query that doesn't actually match any key exactly. So there's no key that corresponds to 505. But in terms of that orthogonal constraint, it's actually not orthogonal to two of these elements. So when I do this multiplication, the dot product of this query and the keys, I get these scores in the first and last spot. So the 505 matches in the first column, so to speak, matches this first one, and it matches the last column in this last entry. So we end up, after the normalization, getting the same effect of averaging the first and last value, even though we didn't match the query to the key exactly. So this is really interesting, because what we're talking about now is this idea that the query can match the keys, all of them to some degree. And then after this normalization, we get this sort of weighted sum of all the values potentially. So this is this soft lookup where we're actually potentially grabbing a combo of all values. Now, there's no reason why the right set of queries and keys can't pick a particular exact value, but this is really interesting that we can sort of have this smoothness around one or many or potentially all as a combo. I'm going to rewrite this one little way using Einstein. So I'll post a link in the comments here for another intro video I did on Einstein if you haven't seen this notation. But just really quickly, rather than doing dot products, I can express this computation a little bit differently to say that I've got a query and key. And when I'm calculating the scores, the query is a 1D vector of length k. The key is a matrix of size mk. And what I want with this reduction operation here is to reduce over those keys to get just m. So just to get basically a vector of 4, which is what the scores are. I do the same with the lookup value down here. And I can actually, when I can normalize in a slightly different way. I can use a softmax instead. So softmaxes are interesting, you know, in terms of, if nothing else, in terms of numerical stability, but in terms of optimization, how we're going to be using this as a building block for a neural network. We often see that a softmax is a better way of doing this normalization, even though the way we've sort of talked about these things so far, for these examples at least, we get exactly the same sort of scoring, because we're looking exactly at orthogonal or, you know, sort of exact things. So we get the same effect as a normalization thing. It's just that this is going to be a different way of presenting smoothness to the optimizer. Now, one thing that's interesting about when we start to do these things in these sort of more compressed forms is, especially with linear algebra, it's really easy for us to start to batch these operations. So if I end up wanting to do multiple queries for some reason at one time, then it's very easy for us to express that computation. I can just add a queue in here to basically say do a batched form, so to speak, of these queries. When I do the scores, I can just basically softmax across the rows. And when I do the lookups, I can again just carry forward this queue that basically says, you know, treat the query as a batch, so to speak. What that means is we can do one pass through this method, but with only a little bit of extra generalization, we sort of get multiple lookups. Now, this idea of being able to do this lookup for many queries at once, not just one, will be useful at the very end. And just as a bit of a side, this is interesting that when it comes to JAX, at least, that it's funny to see that this form of things is actually substantially faster. So if I go back a slide, what I'm doing is I'm expressing these 3 bits of computation as this is a batch sort of form of things based on the cube, size of cube being a batch. I'm doing some scores and I'm doing this other batched type operation. And each of them is an independent operation. But what's cool about JAX is that we have lots of ability to express the way we want to package up computation in such a way that the compiler is able to do lots of nice optimizations under the hood. So actually in JAX, to make things faster, what I can do here is express this lookup again with the non-batched form. So basically when query is just a 1D vector, and actually tell JAX that I want to do this batching across the query using an operator called VMAP. Now this gives the view to the optimizer to be able to optimize this whole thing as a series of ops that you know Q will be carried through, and this is substantially faster. So we get the same effect, but it's much quicker. Okay, so this is sort of the operator we're going to be using going forward, and there's a couple of things I want to note about it. 3 things. Firstly, that I think it's interesting, there's no parameters here. This is not a layer that has learned parameters in the way we normally think about layers. This is just an op, so to speak. It's a way of describing compute that says when you get a query and a key and a value, here's what you should output. So it's just like an operator. Another thing that's interesting about this is that unsurprisingly, these sort of operators, when we think about how a map works, is invariant to the order of the rows of the key and the value. So by that, I mean that if I was to take these keys in these rows and reverse the rows or permute them in whatever way. As long as I reversed or permuted the values in the same way, I'll get the same result. And that's because, a lot of this reduction is around adding, and it doesn't matter what order you add things. So that's interesting. And another thing, again, not surprising in terms of how maps work, but is important for how we're going to be using them, is that this series of operations here is independent on the length of the map. And by length, I mean the number of entries. So whether this has 4 entries or 10 or 20, as long as the keys and values are the same size in terms of that length, it won't matter. Okay, so this sort of operator, unsurprisingly, is available in lots of different places. Not only is it you want to roll your own, but any framework will provide it now. So if you think about Keras for really quickly, there's this idea that if I express these things as NumPy arrays, then straight off the bat, Keras provides a layer for doing this. It's called the attention layer, and it does exactly what we expect. You pass a query and a key and a value, and you'll get your stuff back. Another example, really quickly, from another library called Flax, which sits on top of JAX, is what's called the dot product attention. And maybe there's a slightly different form of how you need to represent these queries and keys and values based on them being a little bit more explicit about things like the batching sizes and this concept, which we're not going to go into here, which the number of heads you're using for attention, which is a thing that we won't really touch on. But the main point I want to get across here is that there's actually a lot of implementations of these pieces that you can sort of grab from somewhere else. Okay, so now that we first talked about this idea of a problem around this encoder decoder, I had this idea of a map, which is this attention sort of idea. How are we going to put these two together? Well, let's go back to that original sequence to sequence problem where I've got an encoder, which is these 3 nodes, and then I'm doing some work of a decoder. So you remember in the last one we talked about this intermediate context that was going from the encoder to decoder had to summarize everything about that sequence for the purpose of decoding. So let's look at things a little bit different, and let's pretend we're up to the nth step of the decoder. What are we going to do? Well, what we're going to do is learn, as part of the optimization, 2 functions which we apply to the encoder, the key and the value function. And so each of these sort of arrows here for the keys and the values are the same. They're like a lot of things in RNNs, they're tied. So what we're going to be learning is a function which maps an encoder state to a thing we're going to call a key, and it's going to map an encoder state to a thing we call a value. And so these 3 keys and values are what we thought about before as the dictionary. So this is the map. This encoder, which has 3 states, has a map of 3 keys and a corresponding 3 values. So that's on the encoder side. On the decoder side, we're going to learn a function Q, which is what we're going to call our query. And this function Q is basically a transformation of this decoder state into something which we're going to call Q. Now we can use this Q and these Ks and Vs according to this tension mechanism to look up from the decoder something from the encoder state to bring back over to the decoder. Sorry. So how are we going to do this? Well, it's like we talked about before. There's going to be this sort of idea of a score first, which is this comparison between Q and all the Ks. We're going to normalize them in some way. So we're going to sort of scale things around so that we get this nice affine combo. And then we're going to look up a value by using those scores to sort of grab particular values. Now, this is something that when we're doing this optimization with the softmax and the idea of this sequence to sequence, often will end up being quite hot in the sense that these scores will sort of, if it makes sense to do so, will favor one sort of part of the encoder state. So one of these particular keys or values will be, quite high in the scores, which means that when we do this combo here, we're mostly picking one value. So this is really handy because now what we can do is we've got this value, which is actually a summary of all the values, but often will be just one value that we can now pull back over to the decoder. So this is now given the network an ability to learn a function, Q, K, a set of functions, Q, K, and V, that allow a shortcut from the encoder side to the decoder. So in this case, if Q was sort of having a high affinity with this K, this value would be the main value that comes across. So the information flow now is from this element, the second element, is a bit more direct to the second part of the decoding step rather than having to go through this context. And those sort of things are really useful. removing the bottlenecks are really useful. And in this case, it's actually freed a lot of what this context means between the encoder decoder, because now it's much more about how do I condition this function Q to look back in the right place, rather than having to remember everything specifically about that particular token, which is common thing in NLP, where we may want to look in a place, but we don't actually care too much exactly about the exact token, more like a positional information. So that's really cool. Attention also gives us this really nice property that we can do nice visualization. So here's a visualization from that 2014 paper that shows sort of this idea of how hot the encoder states are being scored when you're doing decoding. So we've got some French and English here. And what I think is interesting, a couple of things interesting, like we said, we might expect before that the main diagonal is quite hot. So most of the attention sort of goes in lockstep. When you're doing the nth decoding sort of step, you're generally looking at the nth part of the encoder. So this is really, really nicely giving us this idea that we are getting this nice sort of shortcuts between an encoder state to decoder state, but with a lot of flexibility. And here's I think what a really great example of that flexibility is. When we're talking about the European Economic Area in English, the tokens are actually reversed, even though there's sort of a one-to-one correspondence between the sort of forms that are being translated, like area to zone. The actual expression, European Economic Area, is in reverse. And so the attention is actually learnt for that part of the sequence to actually look in reverse order just for a little bit before stepping forward. So that's a really cool flexibility that these sort of mechanisms have. There's also cases where you're sort of looking at two words together in terms of a translation. And this is also common between languages, that the exact form of one word might be conditioned a little bit on another word, particularly based on how we might do things. So that's really cool. And another example of attention that I think is really cool that came straight after this is another form of translation, in double quotes, translating between an image to a caption. Again, this idea that we can have shortcuts in this attention mechanism, but it doesn't have to be between sequences of tokens. It can be across an image. So this system, which does image captioning from this left-hand side to this right-hand side, this is a caption generated by a neural network. As it's doing this decoding of the caption, it's actually through the attention mechanism, we can visualize where it was looking at the image. So while it's writing stop sign, it's actually looking at the stop sign. And while it's, translating road, translating in double quotes captioning, the road, it's actually looking down at the road. So this is really, not only is it really interesting in terms of it gives the network the ability to sort of do these nice shortcuts, but it also provides this interesting visualization where we get a bit of insight into what is otherwise generally a black box. Okay, so one last point I want to go through really quickly is an interesting series of developments around this much more recently, around how we can use this sort of mechanism in different ways in sequence processing. And let's think first about the encoder. So generally when we're doing these types of networks where we have these, LSTMs or whatever, we would often stack them. So we'd have to not just have one encoder LSTM, we'd have a stack of them, which goes off to a stack of decoders. So when we're thinking about this idea of stacking for the purpose of learning these sort of deeper representations, we can think about how can we use attention actually, not between the decoder and the encoder, but across the encoder states itself as a form of learning these deeper representations. So let's think about how we can do that in the encoder. We can have keys and values like we had before. But now what we're going to have, rather than having the query on the decoder side, we're actually going to learn the query function on the encoder side as well. And what that allows us to do is it allows us to say, if I've got 3 sort of tokens in my encoder, I'm going to actually learn how I can learn a new representation of these states based on the combo of all the other ones. So in the same way we did things before. So I could take my Q and I'm going to compare it to all my keys in the encoder state and then choose which values to build a new representation for this middle sort of encoded state. Using and the attention works the same way. It's going to be a combo of myself in this case, my own value, and other values around me. And this would generalize across the sequence pretty easily. So I can do the first one again with the same idea, the Q function, and the last one too. And what's interesting is that for this attention piece, I can actually run them all in parallel. Once I've got the Q and the K and the V values, this is just a single pass. So it's very fast. And this is why we actually introduced that batch form of the lookup that had multiple queries, is because when we're doing this self-attention type approach, we have, if we have n states in our encoder, we'll have n keys and values, and we'll also have n queries. So these sort of things where we can run this sort of thing in batch as a single pass, it is always really great because we can get some mammoth efficiency around this. And what's interesting about this is that we can run this in parallel because it's parallel over the states. And that's a classic problem in recurrent neural networks often. And we still actually have this problem. If we think about how this is being run, we have this recurrent sort of bit underneath. And that recurrent, one of the big cons about recurrent neural networks is that you need to run them sequentially. Everything about this query key and value, as it currently is described, is dependent on the previous states. So we have to sort of, before we can run this really nice optimal version of all the things up here, Q, K, V, we actually have to run these fully, which sort of puts a big bottleneck on things in terms of the ability to parallelize this, because we can't fully parallelize it because of these pesky transitions between the states here. But if we can't just remove them. And this goes back to our idea of the invariance on the order. If I have something like I like ice cream, that's very different to ice cream likes I, even though that's semantically not correct, because of the order. So order in sentences is very important. You get a very, very different interpretation of things if you swap order around. So we can't just ignore this occurrence state. Even though this would make this very, very fast to be parallelizable, we can't throw that, that order away because of that invariance of the keys and values up here. It means that we'd lose information. So it turns out there's a really clever way of putting that information back in though, and it's called positional encodings. So what we can do is we can inject into each of these states basically an embedding that corresponds to the position. So don't learn this sort of method that goes between them, but just use this deterministic value. Some people learn them, but you can just literally deterministically describe them, where you inject these positional encodings somewhere up here basically to get this idea of where you are in the state. And the reason this works is because this positional encoding will be different to this positional encoding. So it's no longer translation invariance when you get up to here because of the mixing in of these encodings. Now, this idea means that this whole thing can be run in parallel now, parallel across the encoder states. And that's very fast. When you can do these sort of things, it really, really speeds things up. And this is the basic building block of the architecture called the transformer. It's this idea that, and this is why it was called attention is all you need, because there's this sort of thought experiment about how, well, if attention is really good and it's super parallelizable, how can we sort of get rid of that recurrent state? If we can get rid of that recurrent state, things can be very fast. It's not actually so different, I guess, to the idea of how WaveNet and this idea of treating these things as convolutionally comes into play. So I think, we didn't talk at all about transform in terms of the decoder side of things. It's just like, this is just one layer in the encoder, but I think it's really, really nice to think about that attention mechanism, just to focus on that for a little while as a form of map lookup, because that idea here where we've got a map that we're looking up, this actually, everything we talked about in terms of the way that attention works actually generalizes to also writing values to a map. So you can use this mechanism in not just reading and writing, but as generally around how memory works. So this gets us now to things like the neural Turing machines and memory networks, which again all use this fundamental idea of being able to store things in a map and then treating these things as differentiable in terms of the keys and queries and values, and then getting a dictionary-like behavior. So that was pretty much my entire talk. Yeah, thanks for watching, and I hope it helped understanding. See ya.